Right, so this is the second part of the chapter 4 lecture, and here I will cover logistic regression. I'm going to start by sharing my slides. So we were at the point where I had finished introducing the first part of chapter 4, and now the next part is logistic regression. So the kind of problem that we want to investigate here, the kind of research question that is used here as an example is um, an experiment where we want to know whether set size will affect free recall, right? So the basic setup of the experiment is that in each, in every successive screen, the subject sees a sequence of words in different positions. So dog, hat, fun, hug. Then they see a blank screen with empty boxes. And then they are prompted to recall a particular word in a particular position. So in this case, they should be able to respond by writing here fun, right? So either they'll get it right or they'll get it wrong. So the response can be either correct or incorrect. So the data is in this data frame. df underscore recall is from the bcog sci package. And so if you look at this data frame, what you see is that there's a subject column. So we have repeated measures from subjects. We have different set sizes, 2, 4, 6, and maybe 8. Just take a look at that. Then we've got 0 and 1 responses, which are correct and incorrect responses, trial ID, and something session and block ID. I don't think we really need any of this. So the important section is here, set size and the response, right? These are the two important pieces of information for the current purposes, okay? So one thing we will of course do as always is that we will center set size, right? So here's the set size vector. Here's the set size vector. We subtract from it the mean of the set size, so we get a centered set size. So that's going to be our predictor. And if you look at the distribution of the different values of set sizes in the data set, this is not the centered values. These are the original values. You see that it's 2, 4, 6, and 8. So what's happening here is that the set size can be, here it is 4. It could be 2 words. It could be 4, 6, or 8 words. So you can imagine that the more the number of words that you have seen on the screen, the harder it's going to be to recall one particular word in some particular position, right? So that's what this experiment is about. It looks like more like a memory task, right? So, okay, so what we should always do before we start analyzing data is to check what the structure of the data are. And so in this particular case, you can see that if you run this command here, you'll see that we have 23 data points for each of the set size levels, 2, 4, 6, and 8, right? So there's repeated measurements here on this. So this will become relevant when we get to chapter 5. But right now we are just going to um, work with the simplifying assumption that we have independent data in the entire data frame, right? So it's a simplifying assumption, not quite right here, but uh, good enough for our current purposes. So what we're actually trying to do here is that we are going to assume a Bernoulli likelihood. That means our responses, the dependent measure is 0 and 1 responses, right? So each row in the data frame is assumed to be coming from a Bernoulli distribution, and the value of the probability of producing a correct response, the value of theta here, is going to be specified by row, right? So every row will have some probability of a correct response, and that will be a function of the set size, right? So that will definitely change with every set size. So basically, what we're going to be doing is we are not going to model the observed 0, 1 responses directly, but rather we are going to model a transformation of the probability of producing a correct response in the nth row in the data frame, right? So what we are going to do is we are going to transform the probability. First of all, we're going to transform it to odds. That's the theta over 1 minus theta is refers to, so if we write theta over 1 minus theta, where theta is the probability of success. So this is the probability of success divided by the probability of failure, right? And this ratio is called odds. So in day-to-day language, we often use odds synonymously with probability, right? This is day-to-day language, right? So in layman's language, we're not in mathematics, but in probability theory and in mathematics, odds has a specific meaning that is different from probability, right? Odds is the ratio of the probability of success to the probability of failure. So you have to be careful about how you use this word and distinguish it from its usage in day-to-day language versus in the formal context of statistics and probability theory. So what we're going to do is we are going to work with the odds, but more specifically, we're going to work with the log of the odds. So this equation on the right hand side of the equal sign is representing the log odds of success. And what we're going to do is we're going to transform this probability to log odds space and then work with this log odds value for modeling purposes. So I will show you how this works. So first of all, let's try to understand what the relationship between the probability theta and log odds space and why we would even do this. Okay, why would we work with a transformation? So first of all, what I've done here is that I've created a sequence going from close to 0 to close to 1, right, with small step sizes. And then, so this is basically all possible values, discretized, of course, right? So all discretized possible values of probabilities, right? And then I have computed the log odds, which is the y here. And so what I'm going to show you now is the relationship between the probability values x and the log odds values y, right? And these are two plots. I won't go through the code here. You can look at it yourself. Show you the end product of these two pieces of code, right? P1 and P2, these figures. What I'm plotting here is shown in this figure. So P1 is this figure and P2 is this figure. And so what I'm doing is in P1, I'm plotting the relationship between the probability. So those are the X values and the log odds, that are the Y values. So what you can see is that the significance of the log odds transformation is that we go from a bounded range of 0 to 1 for probabilities to an unbounded range going from minus infinity to plus infinity, right? So what this allows us to do is to work in an unconstrained space as opposed to being forced to work in a 0 1 probability space, right? So that's what the purpose of this log odds transform is. And this log odds transform has a name. It's called the logit link function, right? The logit link function G is taking as input theta, converting it to log odds, and outputting this eta value, right, which is the log odds value. Now, the inverse of this function would place the log odds on the x-axis and the theta on the y-axis. So that's the inverse g minus 1, which takes as input a log odds value and outputs a probability in constrained probability space between 0 and 1. So the eta values, the log odd values can range from minus infinity to plus infinity, but it transforms those values to a constrained probability space which is what you might want if you want to convert back from log odds to probability space. So that's the significance of these functions. They allow you to go from probability space to log odd space and back, right? So that's this function, the inverse of the logic link is called the inverse logic link, obviously, but it also has this other name, logistic, and that's where the term logistic regression comes from, because of the fact that what we're going to be doing is we're going to be modeling our data in log odd space. Once we model the data in log odd space, we will interpret it back in probability space. This is very similar to what we did with the log normal and the normal distributions, right? We model our data in the log normal space, and then we back transform it to the original scale to make it more interpretable for us as researchers. Right. So let's first look at what the model is going to look like and decide on the priors. So our model, did I even specify the model yet? Sorry, maybe I didn't do this. So, so what will happen here, maybe I should have explained this. I'm sorry about that. But what will happen now is that we are going to, our model will look like this. So we have a log odds dependent variable. We're going to assume that we're going to be working in the linear modeling space again, okay, with the log odds as the dependent variable. And we're going to assume that there's an intercept and a slope, and the centered set size is the predictor, right? So for different values of centered set sizes, we are going to be obtaining posterior distributions for the alpha and beta parameters, right? So therefore, we need to decide on some priors for these alpha and beta parameters. That is the intercept and the slope, right? So that's where we are going. And right, so um, this is the data frame again, just to remind you. Remember, we have centered the set size here, right? And so the model that we're going to fit now is going to be not on the 0, 1 responses, but rather on the log odds for every row in the data frame, right? So, oh, actually, there's a mistake here. I should have put a subscript n here. There should have been a subscript n here. Oh, okay, I will fix this later, hopefully. So, um, or maybe let me just do it right now. This is a bit annoying that that's not even correct now. Sorry about that. Just go here. Hmm, here it is, right? So where am I here in the slides? Now, so what I really wanted to say here was underscore n here, right? So let's see if I can redo this. Right, sorry about that. That was a stupid mistake on my part. Um, I will have to check if the book also has this mistake. All right, so that's our model. So we are modeling every row in the data frame, and for whatever the centered set size happens to be, we can generate a prediction based on the posterior distributions of alpha and beta. We can generate a predicted log odds, of producing a correct response based on the data that we have fit the model to. Now, um, by the way, there is no residual term in this kind of model. So this is called a generalized linear model with a logic link function. Okay. So this is, and also this is also called logistic regression. They're both synonymous. These two statements saying that this is a generalized linear model with a logic link function is the same thing as saying that this is a logistic regression model. Okay. All right. So we are not, there's going to be no residual term like in the standard linear model that we have. We usually have an epsilon term, but there's no such term here, right? That's because in the frequentist world, the way these models are fit is different from using least squares, right? So I discussed that in my linear modeling lecture notes, so which are online on GitHub. I've mentioned them before, so you can take a look at those if you're interested in looking at the more details on this whole thing. So if I go to GitHub, and just to remind you about what I'm talking about here, there's the linear modeling lecture notes here, right? So if you look at my linear modeling lecture notes, github.com/LM, you can see more discussion about generalized linear models here, okay, from the frequentist perspective. So anyway, coming back to the model, so one important consequence of fitting this model is that once we have estimated these parameters, right, alpha and beta in log space, we can always back transform the meaning of these parameters into probability space by using the inverse logic or logistic function. That's where we are going with this, right? We estimate the model in log space, get the estimates in log space, and then back transform to probability space using the logistic function, right? That's the whole point here. And the advantage, of course, of doing this is that now we are basically in a situation very similar to our standard linear modeling framework because we are working in an unconstrained space. The log odds is going from minus infinity to plus infinity. We wouldn't be able to fit a simple model like this, simple linear modeling framework would have to be abandoned if we are going to work in a constrained probability space where the values can only range between 0 and 1, right? All right, so where are we? Yes, so what's going to happen now is that once we've estimated all the etas for every row in the data frame, right, one can always solve for the respective theta probability value, right? So this is easy to do because if you think about this equation now, let's go here, right? If you look at this equation, let's say I have log odd space as the dependent variable, alpha plus beta times centered set size is my predictor. And so this quantity this whole quantity um, amounts to um, a mu parameter. Let's call it a mu parameter because this will be one particular value for every set size, right? So if alpha and beta are point values, right? The estimates of alpha and beta happen to be point values. If I plug in a centered set size value like 0, which is the average set size for in the centered values, then alpha hat, right, is going to be in log odd space. This is log odd space, right? In log odd space, I've got an estimate of the accuracy in log odds when the set size is the average value, right? So now the question is, what's the probability? What is the probability um, of success of a correct response when we have the average set size value? Okay, that's the question I'm about to answer now. Okay, so I'm going to answer this. So if you think about this log odds value is log of theta over 1 minus theta. Here, when I'm using theta, I'm referring to the estimated probability of success when the centered set size is 0. And that is estimated to be alpha. Alpha in the Bayesian framework, the alpha hat is going to be a vector of posterior samples. Okay, so we're looking at, let's say, 4,000 samples of alpha hat here. which represents the posterior distribution. So I'm working with a vector of posterior samples, but the equation still holds. So what I'm going to do is I'm going to solve for theta hat. So let's do that, okay? So how does this work? I exponentiate both sides because the exponential function is the inverse of the log. So I say exponent log theta hat over 1 minus theta hat, right, is equal to exponent of alpha hat. So this is both sides exponentiated, right? This simplifies to theta hat over 1 minus theta hat is equal to exponent of alpha hat, right? So now I'm going to multiply both sides by 1 minus theta hat. So I've got theta hat on one side here and 1 minus theta hat times exponent of alpha hat here, right? Now if I expand the brackets, open out the brackets, right? So I get exponent alpha hat minus exponent alpha hat times theta hat, right? On the left hand side, I have theta hat. So let's bring the thetas together. So I'm going to add to each side exponent alpha hat theta hat. That gives me theta hat plus exponent alpha hat theta hat is equal to exponent alpha hat. All right, so now theta hat is common to both these terms. So I take that out and I get 1 plus exponent alpha hat is equal to exponent alpha hat. And that gives me a solution for in terms of theta hat, right? So theta hat is equal to exponent alpha hat over 1 plus exponent alpha hat. What this means is that once I know what alpha hat is, whether it's a vector or a numerical value, a constant value or something, an estimate, I can figure out the respective probability. So this is the logistic function in action, right? I go from log odds space for any particular value of the centered set size. I can figure out the respective probability using this back transform. Okay, so that's what this equation is. So this is just a restatement. This is just a restatement of this what I just derived here. Okay, the logistic function. So let's go on. Okay, so what's going to happen is our generalized linear model with the logit link function, or equivalently the logistic regression model, fits the following Bernoulli likelihood, right? So for every row in the data frame, we are assuming that there is some probability of producing a correct response. This time, thank goodness, I wrote the equation correctly, right? So with an underscore n. And so the model is being fit on the log odds scale. And once we've estimated the log odds value for any possible value of the centered set size, we can back transform to get the probability value estimated, right? So we will get a posterior distribution. So this is the amazing thing in the Bayesian framework. We are going to get a posterior distribution on theta for every possible value of the centered set size, right? So that's a very important consequence of the Bayesian approach, that we are always going to be working with a posterior distribution of the parameter of interest, in this case, the probabilities. Okay, so there are two functions in R that implement the logit and the logistic function, or the inverse logit function. QLogis will take in as input a probability. Remember, QLogis takes as input a probability and returns a log odds. And plogis is the other function which will take a log odds value and return a probability. So that's the equation I just derived with my derivation just now, solving for theta. Okay, that's the plogis function. Where is it? Sorry. Oh, sorry, I lost my space here, right? So, so now we're going to define a prior for alpha. Just start off with a prior just to see what happens. And what we can do is this prior is being defined in log odd space, okay? So we are talking about log odd space here. So we have a normal 0, 4 prior. 4 is the standard deviation, by the way. And so what we can now do is we can derive some samples of from this prior, which is in log odd space, and pass it through the logistic function to get the shape of this prior in probability space. That will help us interpret whether this prior actually makes sense or not. Okay? So let's do that. So what you're looking at here on the left-hand side is the prior in log odd space. And on the right-hand side, you're seeing the result of back transforming that prior into probability space. And what you see is something very peculiar. What looks like a reasonable prior in log odd space, normal 0, 4, looks really weird in probability space. It's like a horseshoe type of prior with high probability mass on 0 and 1 and low probability mass elsewhere. That usually will not make sense in a modeling situation. You don't want to assume a model which is very likely to produce 0 and 1 priors, 0 and 1 probabilities with high likelihood and all other values being underweighted or close to 0, right? So this clearly suggests, this transformation to probability space suggests that this prior, a normal 0, 4 prior is not a reasonable one, right? So what I would then do is try to look for more reasonable prior. So here's another one. Here's a normal prior with mean zero standard deviation 1.5 instead of 4. And now if we do the back transform, what we see is basically what this prior, normal 0, 1.5, amounts to in probability space a roughly uniform prior over the probability. So this would be an uninformative prior that we could use. So you can, of course, as an exercise, it's good to play around with this a little bit. Try out a couple of other values for, the prior and see what you get. So maybe I'll just do something, okay, just for fun. Let me try this. So the way one could, in a very primitive sort of way, one could produce some log odds, some log odds values from my prior. So I'll say alpha. Let me just call it alpha. So here's my prior from, let's say I take 10,000 samples from a prior with mean 0 and standard deviation 4. That was the first one that I did. And then if I plot the histogram of this in log odd space, I see a nice Gaussian distribution as it should be. But if I pass this through the p-logis function, right? Remember the p-logis function? Where is it? Where is it? Where is it? This one, right? So it will take, this is the inverse logit or logistic function, takes as input a log odds value and returns the probability value, right? Log odds value as input returns probability value, right? So that's what I'm doing now. And so let me do that. I should get this weird shape. Let's see what happens, okay? I've done the p-logis. And so if I plot the distribution, I see the heavy tails here. So now I can play around with the standard deviation a bit. This is how one actually derives priors that make sense, okay? By really graphing them to see if they make sense logically, right? This gives me more of a uniform distribution. What would happen if I change this to 0.5? Right, so now in probability space, I'm downweighting, regularizing the distribution such that 1 and 0, yeah, 1 and 0 have very low probability and most of the probability mass is distributed. I could make this even tighter, right? So I could make the distribution even tighter. Let me just make this more comparable. X lim goes from 0, 0 to 1, right? Right, so now you see that this is a very tight distribution over 0.1. If I increase the standard deviation, then I get a wider distribution. If I make it even wider, right? If I make it even wider, I get a uniform distribution. So you can modulate your you can express your beliefs about the prior range of probabilities for theta by working with this prior with different standard deviations. Okay. So that's how these plots are being brought about. And so this prior seems pretty reasonable for our particular purposes, but you could imagine changing this prior to zero point 0.5, for example, a standard deviation to zero point 0.5 to get a more, regularizing function which downweights 0 and 1 values. That would be reasonable in some context, okay? So now what you can do is you can do your sensitivity analysis with a different range of priors for beta as well, right? So right now I've been talking about alpha. We've settled on this prior for alpha. For beta, we can do a sensitivity analysis as well and study the consequences of using different priors. And here's the result here. You can look at the code in the textbook, but the what you're seeing here is the um, the effect of choosing different priors for beta. Having chosen a prior for alpha, we fix the prior for alpha now. We are choosing different priors for beta, and you can see for different set sizes. These are the original set sizes, not the centered values, of course. You can see that we have different types of prior predictive distributions, right? So, for example, the normal 0 1 prior doesn't seem super reasonable because it produces this kind of distribution of accuracies, producing a larger proportion of 0 1 responses. You see that. So I would not use a normal 0 1 prior. um, these prior so these distributions don't look so crazy, right? But I would probably work with um, uh, one of these two priors because they're reasonably uninformative but don't actually produce crazy data such as this kind of horseshoe shaped distribution of accuracies of correct responses, right? So sorry, let me say that again. It doesn't produce, these other priors do not produce prior predictive distributions of the probability of correct responses in this weird horseshoe shape where 1 and 0 are the highly weighted values. Okay. So one can also use the prior predictive distributions to study for different prior specifications for beta, what the um, what the predicted differences in accuracy would be between different set sizes. So usually, when you're studying a problem like this, what we are scientifically usually interested in is something like this. Just try to sketch it out. So scientifically, what's really of interest here is like when we have, 2, 4, 6, and 8 as the recall accuracy sizes. What we are interested in scientifically is that we would expect some probability of correct responses to be, pretty high. With 2, would go down to 4. With 6, it would go down further. With 8, it would go down further. Of course, this is a fictional plot, but this fall in accuracy is usually what is of interest theoretically when studying memory processes, you know, recall processes and so on. So, so this is what we are plotting here. So what we are looking at, for example, in this plot, in this cell here, we're looking at with a prior on beta being normal 0 1, the difference in accuracy between going from 2 to 4, so the difference between 4 and 2 set size is on average 0%, but it ranges from minus 0.5 to plus 0.5, right? So that's the prior predictive distribution of differences in accuracy for different, combinations of set sizes, of adjacent set sizes, 4 minus 2, 6 minus 4, 8 minus 6, right? And for different priors. So you can see what the implications are of the different priors for allowing a particular range of differences in accuracies between subsequent set sizes, adjacent set sizes. So given this output, A reasonable prior for beta would be a normal 0.01, because if you look here, what we are seeing is that the changes in accuracies between 8 and 6, 6 and 4, and 4 and 2, they are centered on 0, but they allow a certain amount of variation. There won't be dramatic changes in accuracies, right? So a priori, one can assume that if one has some domain knowledge about this problem, okay? So you wouldn't see a fall in accuracy going from 2 to 4 set size, right? You wouldn't see a fall in accuracy of like 60% or something like that, right? That would be a dramatic fall, but you'd see a slight reduction. So this seems like a reasonable starting point, although there's no harm in even allowing more variation and allowing 0 and 0.5. So there's some room for, investigating the impact of more relaxed priors on the beta parameter here. One could do a sensitivity analysis. So anyway, let's just take these priors for now for illustration. Fit the model and examine the posterior distributions on of the parameters, right? So here we go. Now the syntax is for the generalized linear model. It's just the same as the linear model. That's the beauty of the whole generalized linear modeling framework, that we stay in the linear modeling world, right? But we just transform the data. We transform the data so that we are no longer constrained to a probability space, right? We can work in an unconstrained space. So our dependent variable are those 0, 1 responses, by the way, in the syntax for BRM and also in the GLM function in R. This is the intercept and slope, okay? This is all familiar. Here's our data set. The, the likelihood is a Bernoulli because we are modeling these 0, 1 responses, but with the logit link function. So what we write here is family Bernoulli link logit. That ensures that we have the right transformations internally, right? And now there are two parameters, alpha and beta, intercept and slope. And so we set up the priors that we just worked out and look at the posterior summary, right? So let's look at this. So in the this is all now in log odd space, by the way. We are looking at the posterior summaries in log odd space. Now, as human beings, it's hard to interpret what these log odd space tell us, right? So the intercept is telling me the grand mean log odds, right? For the average set size, right? What is the predicted log odds? I don't know what this means in probability space, but I can work it out with the p-logis function. Similarly, I know the I can see the posterior distribution of the beta in log odd space. Notice that it's centered on a negative zero point 0.2 value, which is already telling me that there's going to be a reduction in accuracy with every unit increase in set size, in centered set size, right? That's what that negative sign is telling me, right? But we can do more. We can do the actual calculation. So first of all, from the fitted model, I extract the samples of the intercept. From the fitted model, I extract the samples for the slope, right? So these are the alpha and beta samples. Oops, sorry. And then I compute the mean for the beta sample, okay? Then the lower and upper bounds for the beta samples. And um, right, so I could summarize these quantiles, right? But what I'm showing you now is how I would take the log odds posterior samples for the intercept. So those are the alpha samples, and I would convert them back to probability space, right? So I'm running it through the p-logis function, like I just showed you when I was doing the iPad derivations. I can just put the samples, 4,000 samples, let's say, of the alpha posterior in log odds space, run it through p-logis. That gives me the predicted, the posterior distribution of the accuracy when I have centered set size equal to 0. That means the average set size is the one of interest here. Okay. And so now once I have this accuracy in probability space, this is the posterior sample now. So now I can do statistics on it, like calculate the mean accuracy. This is the mean accuracy when the set size is at its average value. And this is the 95% credible interval. So the beauty of the whole, Bayesian framework is that I can talk about my uncertainty of this probability, right, directly by looking at the mean in the 95% credible interval. Okay. So that's a very big advantage that you can directly talk about how unsure you are about this accuracy, and you can express your uncertainty through the 95% credible interval. That's why that's why we often say that the whole Bayesian approach is all about uncertainty quantification. We're trying to quantify our uncertainty about this parameter. Okay? Right. So now the interesting thing scientifically, as I said, if you think about the figure that I just showed you, so usually what we would be interested in is this fall in accuracy. This fall in accuracy going from 2 to 4, or the fall in accuracy going from 4 to 6, or from 6 to 8, right? That's usually of theoretical interest. So you can compute that now, because once we've extracted the beta samples, that's the slope parameter in log odds space. So what we can now do is we can calculate what we are computing here, this effect middle. What it's computing is the probability of producing a correct response when you're at average set size, and subtracting from it the probability of producing a correct response when you're at the average set size minus one, right? So one less than the average set size. So that's what is called effect middle here, right? This is just a phrase, an arbitrary phrase that's just trying to express this idea that if you're talking about the center point, in the set size, the mean of the set size, what is the change in accuracy when you um, uh, um, increase set size by one, right? You increase set size by one. So the change in accuracy in probability space, remember we are running it through the P largest function now, right? Gives us this this difference, this change in probability in the correct probability space, and so it's a 0.01. The proportion, the accuracy goes down by 0.01 here in this case, with a 95% credible interval shown here, right? So this is a very convenient thing now, because we fit our model in log out space, and we can always figure out whatever quantity of interest we are interested in theoretically by doing this calculation, this back transformation. This should remind you of the log normal transform also. That's also similar to what we did earlier. Similarly, you can compute for what happens when you go from 4 to 2. Okay, from 4 to 2, that means from when you increase the set size from 2 to 4, your accuracy will go down by 2%, or let's say 3%, almost 3% here, right? That's what's happening here. 4 minus 2, right? So this is the same calculation, but what we are doing here is that what this 4 and 2 refers to is 4 and 2 centered. So the mean of the set size is taken, and then that is subtracted from 4. Similarly, the mean of the set size is subtracted from 2. So 4 and 2 are referring now to the centered set size, and these 4 and 2 then are plugged in into the equation, just like I plugged in just as I plugged in minus 1 here, right? I'm plugging in different adjacent sequences of set size, but centered set size now. So I get the reduction in accuracy when I go from 2 to 4, right? That's what this is all about. So basically, the important thing to learn here is that we fit our model in log odds space, estimate the parameters in log odds space, so we obtain posteriors for those parameters, right? We obtain posteriors for those parameters, the alpha and beta in this case. And then if we want to interpret those posteriors in probability space, we just run it through the p-logist function for the relevant centered set size that we're interested in, right? So this is a very general framework. Regardless of how many predictors you've got, if you have multiple predictors, there's a multiple regression problem. It's all fine, because you will just compute through the p-logis function the relevant probability for a particular sequence of predictors, right? So you can do that very straightforwardly. We will get some practice with that later on, right? So that's the whole story with logistic regression. The next topic that I will cover is from chapter 5. We are going to scale up the linear modeling framework to a hierarchical framework. And the beauty of the whole approach will be that the entire hierarchical modeling machinery will apply to all the linear models that we have looked at so far, generalized linear models and the standard Gaussian and log normal likelihoods that we looked at. Everything will be just more of the same. We will just be adding hierarchical structure because we will have repeated measures data, and we need to model that dependent the fact that the data are dependent now, that they are not independent data. In the modeling that I've been doing so far, I've just ignored this problem. The fact that we had dependent data, I just didn't care about it because I was just trying to explain the simple linear modeling machinery. But all the models that I was fitting were technically wrong because they're ignoring the dependencies in the data. So now we'll take those into account in chapter 5.